Okay, we're heading down the home stretch for the course. We're in Module 11, and this is the first, it's Chapter 30 is the topic, and it's the first of two chapters as we wrap things up that are essentially about meteorology. They're about weather, and I really like these sections because I spent a decade as a meteorologist. My background is actually meteorology. I spent 6 years as a television weatherman and 4 years working for USA Today, the nation's newspaper. So you're going to see peppered into the slides a few graphics that I developed during my time at USA Today. Now, the Chapter 30 is kind of a broad look at weather. It's actually kind of a look at climate and how the climate of the Earth is influenced by circulations within the atmosphere as well as circulations within the ocean. Okay, so here's a picture of the globe, and if you recall back in chapter 27, we talked about plate tectonics and the fact that the continents have moved around over time. And in their current positions, notice how much land mass is actually in the northern hemisphere, everywhere north of the equator. Whereas south of the equator, there's actually a lot of just water. There's not a whole lot of land mass. That's actually interesting, and it is kind of a climate driver unto itself. But most of the Earth's surface is covered with water. And water, as is mentioned in the slide here, has a high specific heat capacity. What that means is that it takes a lot of energy in order to raise the temperature of water a little bit. So if you ever tried to boil water on the stove, the reason why it takes so darn long is because water has a very large heat capacity. And that may seem like a bad thing, but it actually is a good thing in the sense that it does moderate the Earth's climate. The Earth is constantly being exposed to sunlight and receiving solar energy. And the fact that it takes a while for that solar energy to register as an increase in water temperature is a good thing. And also the large heat capacity is a good thing because areas that are on the nighttime side of the Earth actually enjoy some of the release of heat energy from the oceans. So again, because of its great heat capacity. So we're going to talk about how the proximity to water influences the climate of an area. So for example, if you live close to the coast, you've got more moderate temperatures because of the moderating influence of the water nearby. The fact that during the daytime it doesn't quite get so hot, during the nighttime it doesn't get quite so cool. And this is a good example of what I was just talking about. This is a graphic that I created for USA Today years ago when the British Open was going on. And the British Open, of course, is held in Britain. In this case, it was at Royal Birkdale Golf Club on the western coast of England. And it's pretty far north of the equator. It's got a latitude of about 54 degrees north, well to the north of the continental US. And yet they played golf. It was in July, and it wasn't sweltering, but it was relatively pleasant. And that had to do with the fact that the western coast of England enjoys a good tongue of warm air, of warm water called the Gulf Stream, that helps to keep that part of the world a little warmer than it would be an equivalent latitude location such as Edmonton, Canada, experiences much cooler conditions during the course of the year. So the Gulf Stream helps to moderate the temperatures in Southport, England, compared to in Edmonton, Canada. Okay, so this whole chapter is entitled The Atmosphere, the Oceans, and Their Interactions. So we need to define what the atmosphere is. The atmosphere are the gases that make up the Earth's air, essentially, which early on in the Earth's formation was mostly hydrogen and helium. But then as there was outgassing from volcanoes, as there was bombardment from comets and such, other things other than just hydrogen and helium became part of the Earth's atmosphere. In fact, hydrogen and helium were easily stripped away from the Earth because they're very, very light gases, and the Earth's gravity is not strong enough to retain those very, very light gases at the temperatures that the Earth has. So the atmosphere has changed over time, as if you recall in chapters 25 and 26, as the plants started to create a primitive form of photosynthesis, free oxygen became available, which then turned into ozone through chemical reactions in the atmosphere. And that was key, having an ozone layer and a protective shield from a lot of the gamma radiation that comes from space helped the development of more complex forms of life. And some of the life that originated in the oceans. Most of the early life forms were in the oceans, and they developed in different parts of the oceans. Now, as we talked about in the plate tectonics chapter, the continents don't just stop at the edge of the land where the land meets the water. There actually are continental margins that are still typically part of the continent. So that includes the continental shelf, the continental slope, and the continental rise. And of course, then when you get into the ocean, then you start dealing with the deep ocean basin. And as we already talked about, the mid-ocean ridges are the locations where new crust is being formed. And then the trenches are where crust is being destroyed. Okay, when it comes to ocean circulation, we can actually distinguish between surface circulations and more deep water circulations. The surface is essentially driven by wind, and you wind up with surface waves. The waves don't really transport the water from place to place as much as it transports energy through the water. So the water itself moves kind of up and down with the waves, and the energy is transported forward. When we talk about deep water currents, well, we're actually talking about motion of water from one location to another, and that's not so much driven by waves, it's more driven by essentially differences in density, and that of course is tied into temperature and salinity and that kind of stuff. But as far as surface waves, you do see these what are called orbital waves that do change shape as they approach a shoreline, which the wave height grows a little bit larger and the wavelength shortens, and you wind up with breakers that crash down on the beach. Okay, the box on page 735 goes through some of the geological landforms that can be created by crashing surf on the beach. One that's most interesting, of course, is the barrier or the sandbars that can form. It's not necessarily mentioned here. Sandbars will eventually form barrier islands if allowed to grow big enough, but little sandbars can actually be quite dangerous if you're out swimming because you could get rip currents that are associated with sandbars. Another box that is in your book is on page 733, has to do with tides, the fact that the moon and the sun to a lesser extent have influence on tides. You know, the fact that the moon has a mass and the earth has a mass, and as we know, any two objects that have mass are going to have a gravitational attraction. So there is an attraction of the Earth on the moon. In fact, that's what keeps the moon in circular orbit around the Earth. And in a similar way, the moon has a pull on the Earth, and they're both equal. Newton's third law of motion says that the force that the Earth exerts on the moon has got to be the same as the force that the moon exerts on the Earth. So how is that force that the moon exerts on the Earth manifested? For the most part, it is manifested by a tugging of the water. So what happens is the moon pulls on the ocean, especially on this side, because the pull is going to be stronger the closer you are. And so the water gets pulled to this side of the Earth, plus the center of the Earth gets pulled in this direction. And this water over here is pulled, but not as much. And therefore we have a difference in the amount of pulling that goes on. So we wind up with a bulge of water here. We have a bulge of water on the other side as the Earth essentially gets pulled away from the water on this side. And so you wind up with two bulges and then two kind of low areas. And as the Earth spins, it's going to, during the course of 24 hours, spinning once on its axis, it's going to move through two bulges and two low areas, and that's where it experiences the tides. So it has essentially two high tides that are about 12 hours apart and two low tides about 12 hours apart. Now, sometimes not all tides are created equal. Some tides are larger than others, and that has to do with the orientation of the moon, sun, and Earth. So notice that when the moon is between the sun and the Earth, that's called a new moon position. When the moon is over here, it's a full moon orientation. But notice that in either new or full, the moon's pull on the Earth's oceans and the sun's pull on the Earth's ocean are essentially, they're pulling in the same direction. And therefore the bulges are really large, and therefore you wind up with what are called spring tides. And here's a graphic that indicates that same kind of orientation. This is a graphic I did years ago where the moon was in its new moon position. So it was pulling on the Earth's oceans, as was the sun, and they both added up together to give larger than normal high tides. Now, when the moon is in its first quarter or its third quarter positions, that means that there's a right angle between Earth, sun, and moon. And so the moon is pulling on the Earth's ocean, and the sun is pulling on the Earth's ocean, but notice that they're kind of pulling at odds with each other, at cross purposes, if you will. And therefore, the bulge that is created is not as large as it could be. Those are called neap tides. Okay, so if you recall the Neil deGrasse Tyson video that I've mentioned several times now, think about the original constituents of the universe, mostly hydrogen and helium. With the Earth's atmosphere, very little hydrogen and helium. As was mentioned, it's very difficult for the Earth to hold on to such light elements. What do we have here on the Earth? For the most part, 99% of what you breathe in is nitrogen and oxygen. And these are elements that are only around because of old stars that have fused small elements into larger elements during the course of their lifetimes. And then when they came to the end of their lives, they exploded their enriched guts into the cosmos, from which the cloud of gas and dust that formed our solar system, it borrowed those building blocks and used them to create the sun as well as the planets. So our atmosphere, primarily nitrogen, oxygen, primarily it is close to the Earth's surface. Our atmosphere, for the most part, is in the atmosphere that we care about is the troposphere. It goes about 10 miles up, 12 miles up in some locations. This is where we live. This is where we spend most of our time in the troposphere, and this is where most of the atmosphere, all those gases, are close to the surface of the Earth. Then we, of course, above the troposphere, you have the stratosphere, and so these are actually in order of increasing altitude until you get to the exosphere. Not that these are not important, but they're not important as far as when we talk about active weather and that kind of stuff. We're talking about stuff that's happening in the troposphere. The stratosphere is mostly important for our purposes because it contains ozone. And ozone, as we have learned, helps to block ultraviolet and other damaging forms of radiation. Okay, so this is a nice chart. It's reproduced in your book on page 720, which shows the temperature of the Earth's atmosphere. And notice that in the troposphere, again, this is the one we care about, temperature does drop off as you increase in altitude, which makes sense if you've ever climbed high in the mountains. It's colder there. Now you'll see that there is an increase in temperature in the stratosphere, and then a decrease in the mesosphere, and then a large increase in the thermosphere, et cetera, et cetera. Keep in mind that the temperature is just the average kinetic energy of the air molecules in that particular layer. Remember that almost all the air molecules are in the troposphere. So in the stratosphere, we see an increase in temperature. That means that on average, an air molecule there is going to have a fair amount of kinetic energy, but there aren't that many air molecules up there. And even smaller number are up in the mesosphere and thermosphere. So yes, an individual might be moving around very, very quickly, but there aren't that many individuals. So it's not like if you would go to the thermosphere, you'd be really, really warm. You'd be really cold because there wouldn't be that many air molecules bumping into you, giving you their energy. So for the most part, you'd be losing energy in the thermosphere. And speaking of energy, how does the Earth get energy from the sun? How does the Earth stay warm? Well, first of all, it does absorb energy from the sun, mostly in the form of visible light. The sun produces all kinds of different types of radiation, but it peaks in the visible end of the spectrum, which is interesting because that's the way our eyes evolved. Our eyes evolved to respond to the type of radiation that is most commonly produced by the sun. But what happens to the people on the night side of the Earth? Are they not warmed at all? Well, fortunately they are. So it's not like we go through periods of great warmth during the day and then great cold during the night. It turns out that the atmosphere also emits radiation all the time, and that radiation is in the form of infrared radiation, and that helps to moderate temperatures overnight. So during those hours that you are pointed away from the sun, you're not receiving direct solar radiation, you're still receiving radiation from the Earth's atmosphere, helping to moderate temperatures during the nighttime hours. And of course, where the sunlight is more intense, that's where you get more solar energy, and therefore those are your hotter areas. So this is a graph that I made several years ago, and so obviously during the daytime, the sun and its visible light rays come down and heat the ground primarily. They don't really do much to heat the air itself. The atmosphere is pretty much transparent to visible radiation, which means that the sunlight comes straight through the atmosphere without being absorbed. It does get absorbed by the Earth's solid surface, which then warms, and then the solid surface usually radiates in the infrared, which helps to absorb, gets absorbed by the atmosphere and warms the atmosphere that way. Obviously, cloud cover does have an impact. So on a cloudy day, the reason why it doesn't get quite so warm is because a lot of the incoming sunlight gets reflected off of the clouds and never reaches the ground, never warms the ground. Similarly, on clear nights, of course there's no incoming light, but the Earth emits infrared radiation. On a clear night, though, it goes straight off into space. However, on a cloudy night, some of that radiation gets absorbed by clouds and re-emitted back down toward the ground. And that's why clear nights are usually cooler. The Earth loses more energy more quickly on a clear night than on a cloudy night. So you may be wondering, why does the sun shine more brightly in some locations and not so brightly at other locations? It all has to do with the fact that the Earth is tilted with respect to its orbital plane. In fact, it's tilted about 23.5 degrees with respect to its orbital plane. And so we have different seasons, essentially. So in the wintertime for the northern hemisphere, the northern hemisphere is tilted. Try to draw my equator in orange here. The top half there, the northern hemisphere of the Earth, is actually tilted away from the sun. Whereas 6 months later, at the summer solstice, the top half of the Earth is tilted toward the sun. And so the sunlight is more intense in the summertime in the northern hemisphere than in the wintertime in the northern hemisphere. And that means that not only do you have more intense heating, but you have longer days as well. And this is a graphic that indicates, shows that tilt of the Earth's atmosphere, of the Earth's rotational axis compared to its orbital plane, and that then means that certain parts of the Earth above the Arctic Circle and below the Antarctic Circle, you can go through periods where you see no sunlight. So in the wintertime, above the Arctic Circle, they have 24-hour darkness. And in the summertime, above the Arctic Circle, they have periods of 24-hour daylight. Okay, so now you're going to get a chance to test some of your knowledge about some of these earthbound climate drivers. So why do we have certain locations that show great extremes in their temperatures and others that are pretty moderate? So think about things like location with respect to water, altitude, etc., as you go through this the skills test. And of course, always keep in mind that there is a video tutorial which will help you work your way through this interface. Okay, if you recall, back in chapter 29, we talked about the Carboniferous period and the Mississippian and Pennsylvanian period, when a lot of fossil fuels were made. And I believe I mentioned the fact that during that time period, a lot of carbon dioxide was locked away in the Earth in the form of these fossil fuels. And we have since the mid-19th century liberated a lot of that carbon via combustion. By burning fossil fuels, we have now released a lot of carbon that took millions of years to lock away, and was locked away for millions of years, all of a sudden is liberated in the span of a century and a half. And therefore we have seen an increase in the amount of carbon dioxide. This in orange here These are records from Mauna Loa, a guy named Charles Keeling has, back in the 50s, set up an experiment and a recording station in Hawaii measuring carbon dioxide in the atmosphere. And then we can even go further back by using ice cores and determine the carbon dioxide concentration further back. And what we see is a steady increase in the amount of carbon dioxide. Carbon dioxide is indeed a greenhouse gas, and therefore it has contributed to an increase in the global temperatures. Okay, now you've probably heard the term atmospheric pressure, and a lot of folks don't understand it. It's usually given on the weather report, and I like to think of it as the weight of the air on top of us. And the analogy I give is if you ever went swimming, all right, and you're at the bottom of a pool. There's your swimming pool. Down at the bottom, what do you feel? If I put one little guy down here, what is he noticing when he's at the bottom of the pool? His ears hurt, right? Why is that? Because he has got a big old, essentially a big column of air right on top of him. And air is heavy. Air weighs about 62 pounds per cubic foot. So you have 12 cubic feet of water on top of you. That's going to weigh a lot. And your ears register that weight as pressure, because pressure is just force per unit area. So all that weight, all that force is being exerted on a small area, your eardrum, and you feel that pressure. Similarly, when we're on the Earth's surface, we're at the bottom of a big old ocean of air. That ocean of air extends, perhaps even just into the troposphere, where most of the atmosphere is located. That's still a good 10 miles high, right? 12 miles high. That's a lot of air. Each individual air molecule does not weigh very much, but you stack them on top of yourself, and they're going to weigh down on you at about 14.7 pounds per square inch. So there's 14.7 pounds of force for every square inch of your body, just due to the weight of the atmosphere on top of you. That's what atmospheric pressure is. And that weight can change. Sometimes this column is heavier, sometimes it's lighter. And that's what weather people look for. They look for changes in the weight of the air on top of you, because that will determine the motion of the air. And of course, motion of air is winds. Air always moves from areas of high pressure to areas of low pressure. Okay, so what actually drives air then? What creates these differences in pressure? It all has to do with the uneven heating of the Earth. The fact that the equatorial regions tend to get more heating during the course of the year, and the polar regions tend to get less heating. So that the difference in heating drives differences in pressure. Differences in pressure drives the motion of air. So air usually flows from high pressure to low pressure. As is shown in figure 3010 on page 726, if the Earth wasn't spinning and if it wasn't tilted, you would essentially have a lot of heating at the equator, no heating at the poles, or very little heating from the poles, and it would be pretty easy to have a circulation that would just go from the equator up to the poles, and that's and so forth and so on. But the Earth is indeed spinning, and so therefore you have actually a more complex circulation, what's called a global circulation, where you have different cells that set up. Hadley cells and Fennel cells and all that kind of stuff, which then sets up certain areas where you have winds that tend to blow from certain directions. You have the trade winds, you have the Horst latitudes, and the westerlies, and all that kind of stuff. Because not only is it the pressure gradient force that drives winds, but actually the Coriolis force also tends to affect the motion of winds. So winds don't go straight from high pressure to low pressure. You have to take into consideration friction between the Earth and the air, as well as the Coriolis force, which is due to the rotation of the Earth. Okay, so to wrap up air circulation, again, areas of low pressure, you tend to have low density air, which rises. And so this is actually a side view here. So air is rising. And of course, nature doesn't like having nothing there. So if the air rises from the surface of the Earth, then air from the surrounding regions has to move in and take its place. And then that air, if it's still being heated, rises as well. And similarly with high pressure, you have essentially air that's sinking and hits the ground, has nowhere to go. It's got to go outward. So, and essentially that's what things would look like right here. You have air moving outward from high pressure. You have air moving inward into low pressure if the Earth was not spinning. And if there were no other factors, things would just move straight from high pressure to low pressure. It would be very simple. But that's not the case. We actually have contributing factors of the Coriolis force and friction, which means that around high pressure in the northern hemisphere, winds do go outward. They go outward and clockwise, and they move toward low pressure inward and counterclockwise, and just the reverse in the southern hemisphere. If you recall, because remember at the beginning of the notes I showed you that graphic about the British Open and the fact that the Gulf Stream helps to warm that part of England that normally would be much cooler. And that's all. The Gulf Stream is just an ocean current. It moves water from the warm latitudes, from the tropics, toward the non-tropics, the higher latitudes. And that's all due to the fact that deep ocean currents are essentially driven by differences in density. Density depends upon temperature, salinity, etc., etc. So here's a look. It's kind of a reverse look. Here's the east coast of the United States. Here's Florida. There's the Gulf of Mexico down here. And you see this orange and red and yellow. That's warm water. And notice how that warm water is moving up into the North Atlantic, where it's relatively cool. And so therefore, you have the moderating effect of the Gulf Stream. Okay, so now you've gotten a pretty good grasp on what drives motion in the atmosphere and in the ocean. Go ahead and take a swing at the lab activity. Again, as always, there's a nice tutorial video which will help step you through the simulation. And of course, go to the end of Chapter 30, check out the readiness assurance test, and take a swing at those first, and check your answers with the answers here on the list.